Good afternoon. Just checking if you are hearing me clearly.
We're hearing, sir.
Are you hearing me?
Yes, sir.
Are you hearing me? Good evening.
Evening, sir.
All right.
Good evening, sir.
All right. Good, good. All right. So for the first half an hour, we're just going to run back through some stuff, and then we do the past paper questions. All right. So as usual, here we have a table. So using the information from the table, deduce the order of the reaction with respect to x and y. So I'll give you 2 minutes to answer part one, part A and B. All right, so one A and B, 2 minutes, and then I work it out. We'll put on the timer.
Sir, you can move the timer over to the next
Oh,
slide.
sure. All right. So anybody, what is the order of reaction with respect to x?
First.
First
Sir,
order.
your second order.
Hold on. X is which one? Is it first or second? X.
Second, sir.
All right. So I heard first order, and I heard second order as well for x. All right. So if we, all right, Regina, which two experiments did you use for x?
2 and 4.
All right, so I use experiments 2 and 4. All right, so in experiments 2 and 4, the concentration of X, it increased by a factor of 2. And what happened to the rate? It increased by how much?
4.
Right. So remember, when for second order, the rate is proportional to the square of the concentration. So when the concentration doubles, so when concentration doubles, the rate, it goes up by 4. So concentration goes up by 2, rate goes up by 4. So second order is correct. All right. For the person that said first order, why did you say first order? So I
Sir,
can.
I keep mixing up, and sometimes I'll look at, I thought I was supposed to look for X to find X. I thought I was supposed to look at the two same concentrations and then
Oh,
find, yes, so I mixed it up.
right.
Understand now.
All right. So for anyone watching, if you are seeing this for the first time, right, we're calculating the order of reaction. So in order to do that, so for example, we want the order of reaction for X. So we have several experiments here. So we look for 2 experiments where we change the concentration of X. But for those 2 experiments, the concentration of Y must not change. So if you look at experiments 2 and 4, the concentration of Y, it stays at 2. So the concentration of Y for experiments 2 and 4, it stays at 2, while we double the concentration of X. All right. So the concentration of the reactant we're interested in, it must change while the other one stays the same. All right. Alternatively, if we did not use experiments 2, we could use experiment. Which other 2 experiments could we have used to figure out the order of reaction in terms of X?
1 and 3.
1 and 3, right? So also, as anomaly showed, right? So comparing experiments 1 and 3, right? We divide experiment 3 by 1, all right? So in terms of concentration, it would be 1.5 divided by 0.5, which is 3. And in terms of the rate, it would be 90 divided by 10, which is 9. I remember we said the rate is proportional to the square of the concentration. So basically, if you square whatever we did to the concentration, right, the rate should be proportional. So if you look, we tripled the concentration. So 3 squared is equal to 9. So the rate is proportional to the square. All right, so good job, second order. All right, so this is in terms of, let me scroll down. So 1A, so in terms of X, that is second order. All right, in terms of Y, what is the order of the reaction?
First order.
First order, that is correct. All right, which 2 experiments did you use for compound Y?
1 and 2.
All right. So in 1 and 2, let me just erase this. All right. So for X, we're using experiments 1 and 2. All right. So in terms of concentration, it would be 2 divided by 1, which is equal to 2. And in terms of rate, it would be 20 divided by 10, which is also 2. So in this case, the rate is directly proportional to concentration. Concentration was doubled, the rate also doubled. All right, so good job there. All right, so X was second order, Y is first order. So and what would be the overall order of the reaction?
3.
Right, so 2 plus 1, 3. All right, what would be the rate equation?
Rate equals K times the concentration of X squared times the concentration of Y.
All right, that's good. So rate equal K X squared. So again, just in case anyone seen this for the first time, for the rate equation, we have rate is equal to K. So K is always there, which is the rate constant. And then you put the square bracket means concentration, right? And then this now, the 2 is the order of the reaction, right? So Kx squared times Y. So Y is first order, so a 1 could be there, but you don't have to put the 1, all right? So you can put the 1 there, but you don't have to. But the 2 must be there, all right? So for the purpose of explaining, all right, I can leave the 1 there, all right? But it don't have to be. Okay, right, so that is our rate equation. And then after that, now, I ask you to calculate the value for K. All right, so as usual, all right, let me see who is here first. That's Regina, Georgia, Anna. All right, Anna, you can use experiment 1, Regina experiment 2, and Georgia experiment 3, and I will do experiment 4. All right, so that's, let me see, rate is 80. All right, so if rate is equal to kx squared y, and we're calculating k, I need to get rid of x and y. So I'm going to divide this side of the equation by x squared as well as y. And whatever I do to this side of the equation, I will also do to over here. And I am using experiment 4. So when we're doing this calculation, we pick a specific experiment from the table and use the data. So I am using experiment 4. So from experiment 4, the concentration of X is 1, the concentration of Y is 2, and the rate is 80. All right, so K is equal to K is equal to 80 divided by 1 squared times 2. So that's 80 divided by 2, which is 40. Do you get 40 for your answer as well?
Yes, sir.
All right.
Yes, sir.
All right, good. All right, I will give you, let's put a time on the board, 2 minutes to work out the units.
Sir, are the concentrations of X and Y in moles per dm cubed?
Right, yes. Oh,
And the
so
rate is
remember,
in meters per second?
right. So the capital M here, remember it stands for, right, so capital M, it stands for moles per dm cube. All right. So if you say a capital M, it is moles per dm cube. All right. So this here is moles per dm cube per second.
Yes, sir.
All right. All right. So timer is up. Give me a second. All right. What did you get for your answer before I work it out? And want to share the answer?
DM.
So let me get my pen. Um, don't. Just a second. So part 3. All right. All right, go ahead now. So I said the unit is
dm6
DM6
mole
mole.
-2
Mm-hmm.
second -1.
All right, that is correct. All right, so let's just look at what we did here. All right, so we have K is equal to the rate divided by. All right. So basically, K K is equal to the rate. Right, hold on. Let me do it here again. K is equal to rate, and the unit for rate is mole per dm cube per second. So the S for second has to be a denominator. So when you see moles per dm cube per second, these are denominators in a fraction. So dm cube is below. The minus here is this line. The minus here is this line. So 1 over S, all right? Moles over dm cube. So all of this is rate. Okay, let's go across. All right, so it's rate divided by x squared. No, x squared, the concentration, that would be mole per dm cube times moles per dm cube. So that's for x squared, all right? But we also have to times it by y. So it's a next moles per dm cube. So as usual, we're going to change the multiplication sign, the division sign to a multiplication sign. And then everything over here will flip. So it becomes dm cube per mole, dm cube per mole, dm cube per mole. And over here, it stays as is. Mole per dm cube. So dm cube cancels dm cube, mole cancel mole. All right, so dm cube, that's dm6, mole and mole. Remember, mole is below the line, so it becomes minus when we're putting it in the, when we're writing the unit. So it's mole -2, and we still have the 1 over S here, so that's S minus 1. So you're correct. All right, so that's that. All right. One more thing quickly before we do the past paper. I'd say I have reaction mechanism as well. But this I'm going to do in detail on Saturday. But there's a question on it, multiple choice, not anything difficult. So I'm just going to spend like 3 minutes on this. So here we have an equation, right? So a mechanism is different from an equation. So a mechanism, it gives a more detailed process or a detailed picture of what happens when each compound react with each other. In this case, chloromethane and sodium hydroxide, right? And the same thing here, we have a next equation. Now, what this equation does not tell you is that the first step, right? So as I said, I will go through this in details. But when you react these two compounds, it does not occur in a single step as the equation is showing here. It it occurs in multiple steps. So the first step, the chlorine will come off. All right. Hold on. So yes, so CH3, Cl, and they will end up with this. Now, question: when you look at the equation, right up here, do you see this in the equation? Hold on. Look at the equation and tell me if you see this intermediate here. Is it present in on the left or right hand side of the equation? Yes or no?
So can you repeat the question?
Right. I was asked this that I have highlighted in red. Do you see it in the equation up here? So this here, all right, this, is it the same as this?
Not exactly.
No. All right, is it the same as this?
No,
No.
sir.
All right. So the mechanism is showing you that when these two compounds react with each other, there are things that are formed that the equation does not show. All right. So the good thing I'm going to tell you in terms of to answer the questions, you see this first step here, it is the slowest step. All right. Now, because it is the slowest step in this mechanism, oh no, sorry, it is the slowest step. All right. And so, because it is the slowest step, it is the step that will determine, it is the step that will determine the rate of the reaction. Notice this hasn't come into play as yet, right? So the first step in the mechanism, that is the step that will determine the rate. So we call this step the rate determining step. Rate. All right. Whenever we write a rate law, right? If you remember in our previous classes, we said that you cannot determine how the constant, you cannot just determine the rate law from like an equation. You have to do it by experiment, all right, to see how each reactant affect the rate. So you see, because this mechanism here, it has more than one step. This step right here is what is going to go into our rate equation. So from this, my rate will be equal to K times the concentration of this compound. I'm just going to call it compound A. All right. So rate will be equal to K times A. Notice the sodium hydroxide is not in the rate equation. The reason for that is it is not a part of the rate determining step. All right. So if it's not a part of the rate determining step, it cannot be a part of the rate equation. So for now, that's all I want you to know. But on Saturday, I will explain it in more details. All right. Just remember, The first step is the rate determining step. And whatever is used, whatever reactant is used, that's the only one that goes in the rate equation. So this compound here, it would be the only one that you put in bracket, not the sodium hydroxide. All right. For this one, for this equation here, it's only as one step. All right. Only as one step. So this one down here, it has multiple steps. Okay. So because it has multiple steps, only the first one goes in the rate equation. But because this one only has one step, then the rate law, rate is equal to K times CH3Cl NaOH. What that means, your rate, because it only has one step, both of them are in the rate determining step. That is why both of them are in the rate equation. So if you look down here, only this would be in the rate equation because only it is in the rate determining step. In this one, both of them will be in the rate determining step. So both of them are in the rate equation. All right. So for now, whatever is in the rate determining step, that is what goes in the rate equation. All right. So that is what I want you to get from this for now. On Saturday, we're going more details. All right. So let's go to the past paper now and do some practice.
Sir, can you go back to the first table so I can take a picture, please?
Please repeat.
The first table.
Where is it? Oh, over. Hold on, give me a second. Where was it? This one?
Yes, sir.
All right.
Thank you, sir.
You're welcome. All right. So, and then finally, this here. Hold on. All right. So on Saturday, we're going to look at graphs as well. But just to do the multiple choice now, if you get a graph for rate versus time, this is our zero order graph will look. Remember, with the zero order, rate will not be affected. It will stay the same. With first order, rate is directly proportional to the concentration. So you will get a straight line. And then this is second order. So when it is rate versus time, this is how the graphs will look. If it is concentration versus time, this is how they will look. All right. So they will appear on the questions we're going to do now. All right. So let me just pull that up now. All right. Are you seeing the questions?
Yes, sir.
All right. So this one is from '07. All right. So if we look, all right. So it says item 16 refers to the following reaction which occurs in the presence of dilute acid. All right. So it says if the rate, all right, so we have the ester here reacting with iodine. All right. So if the rate equation for the reaction is rate is equal to K times the concentration of the ester times the concentration of the hydrogen ion. Which of the following best illustrate the slow step? So remember now, let me just quickly switch. Right, I'm not going to switch again. If you remember, well, let me just make it as a note. I create it as a note. Okay. Fine. All right, there we go. Whatever is in the rate equation, that was in the rate determining step. All right. So remember, so the slow step, whatever was in the slow step, that is what will be in your rate equation. So if these two are in the rate equation, what is the answer? Is it A? Is it A, B, C, or D?
A, sir.
A, right. Whatever is in the slow step of your reaction mechanism, that is what will go in the rate equation. So the fact that it is these two that are in the rate equation, then that is what would have been in your slow step. Right? Were we clear on that?
Yes, sir.
Right.
Yeah.
Yeah, so not because you say iodine in the equation mean you're going to pick one with it. All right. So I'm going to scroll down. I will send you this after we are finished. All right. Right, let me see if you remember your graphs. Not your Maxwell Boltzmann distribution curve. Alright, let me zoom back in. Alright, so it says which of the graphs below best shows the change in distribution of molecular energies when a gas at T1 is heated to a temperature T2. Alright, would it be A? Would
No,
A?
sir.
No, sir.
Alright. So first things, when we're doing this type of graph, right? Okay. Do a better, see if I can do a better job there. All right. So this would be T1. And as we know, if we're going to do T2, when we increase the temperature, the peak of this graph must drop, right? And shift to the right. Okay. So observe, right, so this would be T2. So look at B, C, and D. Which one do you think the answer is?
B, sir.
B.
B, sir.
B, right? It could not be C because notice the peak is at the same, right? And we know that it's supposed to drop and move over. This one, it dips, but it doesn't really shift. All right. So let me just remove those. All right. All right. And so, hold on. Let me just take off those. All right. So we said the answer is B. Do you remember how the graph should look for first order when it is concentration versus time?
Sir, is it D?
C. But that's okay because I just showed you a while ago. All right. But it will be C. All right. Right, I will give you a chance to answer this. So, what do you think it is? So, it says which area represents the additional number of molecules having the activation energy at a higher temperature T2. So here is X and down here is Y. So which area represents the additional number of molecules having the activation energy?
X,
X,
sir.
sir.
X is correct because T1, this curve here is for T1. So everything down here is T1. So up here is T2, but the activation energy, as you know, starts here. So you're correct. On the up here in green, have additional number of molecules with the activation energy. So it is X. All right, good job. All right. This one says now an increase in temperature by about 10 degrees Celsius usually doubles the rate of a chemical reaction. This is because, all right, which of these options seems plausible?
A, sir.
Just a second. All right. Everybody agree with that? Or any other options?
Sir, can you zoom out a bit?
Yes. Is that better?
Yes, sir.
All right.
A, sir.
Yes, A is correct. So, all right. Both of you are correct. All right, so let's go to the next one now. All right. Can you see it clearly, or I should zoom in a bit? All right, I'm going to zoom in a bit. All right. All right, so I will give you a chance to answer it. So, what is the overall order of the reaction? Okay, so before you answer this, tell me the order of reaction for with respect to A and B before you tell me the overall order.
Sir, the order of reaction with respect to A is first.
Okay, so double down. Okay, yes.
And the order of reaction with respect to B is 0.
All right. We're all agreeing with this.
Yes, sir.
All right.
Yes,
Yes,
sir.
you're correct. So the overall would be 1 plus 0. So that's 1. Let's scroll back up. All right. So the overall order would be a first order reaction. All right. Well, let me clear this off the thing. So when I save it, it's not there. All right. So first order. So this one I was asking which of the following diagrams represent the effect of an increase in temperature from 70 to 80 degrees Celsius?
C.
Sir, C.
C is correct. So first thing, T2 is before T1 in front of this side. couldn't be this. And these two are just way off. All right. What would be the rate law for this? Sorry, what would be K, the units?
Sir, D.
D, right? So basically, when the overall order is third order, this will be the unit, DM6. So it doesn't matter if you put the DM6 first, all right? So mole, just like we did earlier, mole minus 2 DM6 S minus 1. So this will always be the unit when the overall order is 3.
Sir, when you're writing the rate equation,
Yes,
um, the reason why you knew that B was a first order is because when it's a first order, you just don't write anything above it,
wait,
and when it's zero order, you don't write anything at all for B.
just for which one?
That we just did a while ago.
Down here?
Yes, sir.
All right. Ask the question
How
again.
did you know that B was a first order, not zero?
Oh,
Because
all right. So you see, if for zero order, so let's say B was zero order, rate would be equal to K B 0. So we always put the order of the reaction up here. But anything raised to the power of 0 would give a 1. So basically it is K times 1. So if it's 0 order, we just don't put anything except K. So for 0 order, rate is equal to K. Now for first order, as I told you, you could put the 1, but you don't have to. Alright? So when I say rate equal Ka squared B, B is first order. Alright? So the only one you must put the number for is when it's second order. Does that clear it up?
yes, sir. Thank you.
Alright. You're welcome. Alright, so let me just undo these. Alright, so we said it would have been D. Alright. This is a repeat. Alright, so some of them are repeats. So I just cut anything I saw on rates from '07 to '20. Well, to 2020. All right. This a repeat? Yes, this repeat as right. This repeat. Which year is this? 2010. Okay. So they repeat a lot. So this is an X. So if you work the past paper by topics, you realize the
Sir, I
question.
hear the answer.
Oh, thank you. Yeah. If you work them by topic, you realize the questions they don't really change that much. All right. Answer question 17, because this again, I repeat, which year is this now? This was 2020. All right. What is the answer for question 17?
C, sir.
All right. Because for A, basically, in defining rate, we should be able to measure it, right? So we can measure the rate of formation of a product or the rate at which our reactant is consumed. But the product is not consumed, it is the reactant that is consumed. So you are correct. It's C. All right. And then for this now, it refers to the refers to the following graphs for the reaction between P, Q, and R. So we know that rate is directly proportional to concentration for a first order reaction. For zero order, rate is not affected by changes in concentration, so you will not see an increase. And we know that this one is second order, right? However, how would you interpret why do you think this one is a straight line? Let me see if you pay attention to details.
Sir, mean it directly proportional.
To
The concentration
Square
direct.
of the concentration.
right, that is it. This one rate is proportional to the concentration, so it's first order. But this one, it's actually square of the concentration. So when rate is proportional to the square of the concentration, which order is that?
Second.
Right,
Second.
right. So second order. So this one is the square of the concentration. This one is just the concentration. And this one is 0. All right, so what would be the rate equation? So P is first order, Q is second order, and R is 0 order. So which of these is correct?
B, sir.
B, right. So remember, when it's so for 0 order, rate, all right, so this is it. So rate is equal to K. For this, rate would be equal to KP, and for this, rate would be equal to KQ. Rate would be equal to KQ squared. All right. So we just look for that in the equations. So B KP squared. All right. So B is the answer. Mm. All right. This one now, it says item 17 refers to the table, to the following table. So in this reaction, X produces Y. So we have time and we have concentration. All right, so for this one is tricky. Let me see if you remember. All right, I'm going to give you a hint. All right, it has to do with half-life. So remember this formula T a half is equal to ln2,
Over K, sir.
right? Oh, the reason why I use this formula, by the way, they told us that the reaction is first order. So we have what we call the integrated rate law. We are going to do it on Saturday. So half-life, the formula for half-life is different if it's second order and 0 order. So this is the formula for half-life for a first order reaction. All right. Yeah. So this is the hint I'm giving you. This is the formula. So I will give you 2 minutes to just process it and see if you can answer it. All right, let me remind you of something because you probably don't remember. All right, so half life is the time taken for the in this scenario. Half-life is the time taken for the concentration of X to drop to half. So how long did it take for the concentration of X to half? So what is the half-life of X?
Sir, I have an answer.
Please repeat.
I have an answer.
Okay, go ahead.
Okay, so for the half-life, I got 10 seconds. And for K, that would be ln2 over 10.
Right.
So that would be 0.069.
That is correct. All right, tell us how you got 10.
Okay, so it's at time equals 0 seconds. There were 0.2 moles per dm cubed.
Right.
And if you look down to 10 seconds, where time equals 10 seconds, the concentration had halved to 0.1.
Right, so 0.2 divided by 2 is 0.1. So when the concentration is halved, it should be 0.1. So when it became 0.1, as I said, it was now 10 seconds, right? All right, so from 0 to 10,
Yes.
that's 10 seconds. And if you check again, 0.10 divided by 2 would be 0.05. So from 0.1 to 0.05, that's another 10 seconds. 10 seconds there, 10 seconds. So you're correct, the half-life is 10 seconds. And ln2 is equal to 0.693. So for persons watching, ln2, that's just like you have sine and cos. There's a button on your calculator that marks ln. So you would press ln and then 2. Or if you can just memorize it, so ln2 is 0.693. So in our working out, 0.693 divided by 10 seconds, and you would get 0.069. So good job. Who was
Sir,
that? Yes.
sir,
Go
can
ahead.
you explain over the K, please?
The K.
Yeah, the constant.
All right. Wait. So we're calculating K, right? No. In the table, all you got was time and concentration. So the formula we would have to use is the one for half-life. So the half-life is ln2 over K. So we would have to transpose it. So K, when you transpose it, K comes up here and this comes down here. So K is ln2 divided by the half-life. Understand? Was that
Yes, sir.
the issue?
Yes, sir.
All right. So that is all. And in terms of the unit, because I think there was a next question. I don't remember if it's in this, but I think I saw it. So they are 0.069 S and 0.069 per second. In this case, the time is below the line. It's a denominator. So once it's a denominator, it has to be -1. All right. So yeah, it has to have the -1 there. Okay. All right. So let me just clear this working out. Do you want the working out on the page or erase it? Because I'm going to send it afterwards.
Sir,
Leave
make
it,
it.
sir.
All right. And for this one, let me go back. Right, so we have this is a repeat. Right. Right, so for this one, it says, which of the diagrams above represent the effect of an increase in temperature from 70 to 80?
See.
Right, so we all know this by now. Right. This is repeat again. All right, so the activation energy of a reaction, which of these is correct about the activation energy of a reaction?
Sir,
Please repeat.
Is it
it.
If it's A, no, so A says unaffected by catalyst. So what do we know about the effect of catalyst on activation energy
It
of a
lower.
reaction?
It
Right.
lower the activation.
And this says it is unaffected by a catalyst. So it could not be A.
See, sir.
C says is affected by temperature. Well, in terms of being affected by temperature, if you increase the if you increase the temperature, it would increase the energy of the molecules. So more of them would have the activation energy. If it's from that perspective. But for me, B, what about B?
sir? I
Yes.
had said B.
Oh, I didn't hear. So in terms of the answers, right? When I say affected, but if you look at, so B would be a more appropriate answer because we know it is a definite energy barrier to a reaction. So and we know that if you increase temperature, more molecules are able to surpass the energy barrier. So it is definitely affected by. Remember with the
What do you mean
Boltzmann
by
curve?
energy barrier?
Sorry, please repeat.
Sir, what do you mean by energy barrier?
All right. So for any so with the collision theory, right? For a reaction to occur, all right. So energy barrier. Just imagine it's an admission fee, basically, for the reaction. So when for molecules to actually react, they have to collide with a certain amount of energy. So not every collision will lead to a reaction. There's a specific amount of energy that is needed. So when we say it's an energy barrier, it's because the molecules have to collide with a certain amount of energy. So if we look back at not this graph, let me scroll back up a bit and show you what we mean. Right, this. So if you notice the x-axis as the energy, right? You see all the molecules in this area, they will not lead to a reaction. This line here, this would basically be the energy barrier. So EA, that is the activation energy. It is the energy barrier, meaning only molecules with this energy or greater can lead to a reaction when they collide. Is that clear?
Yes, sir. Thank you.
Right, yeah. So that is what this graph shows. So all of these molecules out here, they will be colliding. They can collide in the correct orientation, but it will not lead to a reaction because they do not have the activation energy. All right. So it's the minimum amount of energy needed for a reaction to occur. Yeah. So that is what we mean by an energy barrier. Just like if you don't have the admission fee to go into a party, you cannot enter. It's the same thing here. If they don't have the activation energy, no reaction will occur. Alright. So you're good now, right?
Yes, sir.
Okay. Where were we? Alright, so we said C. And we passed that. On this one. Okay. And that's 2012. Oh, it was actually a repeat for 2014. Again, this is a repeat, but let's just circle it. Right, for this one now. So we have a reaction. Sorry. So they give us the rate law KAB. If the half-life is 253 seconds, what is the value of K? So they give you the half-life. T half is equal to 253 seconds. Right? How would we calculate K? Any ideas? Once you get half-life, which formula should you use?
A equal ln over.
Oh, sorry. So, all right. So first, the original formula, half-life is ln2 over K. And so if we want the what now, K, what would be K if we transpose?
Ln over half-life.
All right, ln2 divided by half-life. And we know that ln2 is 0.693 divided by 253. How much you get?
Sir, answer D.
B. All right. Why not C?
Because it miss the negative one.
Right. Good. Mhm. Right, good job. Right. What is the effect on a chemical reaction of introducing a catalyst?
A, sir.
Right. Again, we have a repeat here. Same D for the answer. This was 2015. And this was a repeat. What was the answer again for this? B, formation of product. Repeat again. This is a lot of repeat. We
Sir,
could at
wait,
least
C.
Wait, that one was actually C, the rate of
wait.
consumption.
Wait.
On the third, no,
TCP?
it was wasn't
Oh, thank you.
wasn't that
Right.
one the rate of
Right.
consumption of
Yes.
product?
Right. Thank you. Yes. That's why it's good to be careful. And nothing has changed in this, so it is still first order. I could at least change the numbers in the table. So that was 2017. Oh, that was from 2010. All right. From CSEC, right? You just did CSEC a couple months ago. Which of these apparatus would you use to? All right. So let's read the question. So it says, John plans to measure the rate of reaction between calcium carbonate and dilute hydrochloric acid. So when you react a carbonate and an acid, what will be produced? Anybody remember?
Carbon dioxide.
Right. That's the important one. But we can do the equation still. So let me do it up here. So calcium carbonate plus hydrochloric acid will give calcium chloride, water, and carbon dioxide. So we can collect the gas. So we can measure how quickly the gas is produced. All right. So which of these then can you use to collect the gas?
B, sir.
Right. So inside here, you would have the hydrochloric acid and the calcium carbonate. And so you could say time it for 30 seconds. All right. And then the gas produced, it will go in here and you could measure it. All right. So B. All right. So for this one, all right. So we have the equation here. This is at 629 Kelvin and a concentration of 2 moles per dm cube. The rate of decomposition of hydrogen iodide. What is this? To the minus, that's 3 or 5. I think it's 3. I think it's 3. Let's work with 3 and see. Alright, so we're going to work with 24 times 10 to the minus 3. So we have the concentration and we have the rate. What is the rate constant? So we want K. So we have the rate equation already. So HI squared. So quickly, just work it and tell me what you get. All right, so it would be K. Let's see. So K would be equal to the rate. All right, so 24 times 10 to the minus 3 divided by 4. So 2 squared, that's 4. All right, let me just put 2 squared in bracket. And I got A. All right. Anybody else get A?
Yes, sir.
All right. And this again is a repeat. Oh, so you see, this time now, when they repeat it, they change it with the units, with the S and S to the minus 1. All right.
Sir, for the one you do before, the two at the bottom is the order of reaction.
Wait, hold on. No, the 2 is the concentration. And so the concentration is 2. And then this 2 here is the order. Because remember, it's HI squared from up here. So K is HI squared. So it's second order. Right? So it's just coincidence that the order and the concentration are the same numbers. Is there anything else remaining? All right, this is also a repeat, and that, okay, this was B. All right, and so that is it for the rates of reaction multiple choice questions from '07 come up. From '07 to 2020. 2016 was a repeat of questions. I didn't cut any from that. All right, so that's it for this session. All right. And so we will pick up on Saturday by looking at these graphs and the other and half-life for the other orders of reaction. All right. So I'm going to end it here. All right. Have a good evening.
Thank you,
You too,
Lucinda.
sir. Thank you.
Thanks. Bye.